everyone, this is Kamiti. This is Kamiti e-learning platform, and today we are looking at simple stresses and strains. Now, the question of the day is as follows. A steel wire 2 meters long and 3 millimeters in diameter is extended by 0.75 millimeters when a load P is suspended from the wire. So we don't know the value of the load P, but we are going to determine it. If the same load is suspended from a brass wire 2.5 meters long and 2 millimeters in diameter, it is elongated by 4.64 millimeters. So when the same rod P is suspended from a brass wire, the brass wire is suspended or is elongated, by 4.64 millimeters. We are supposed to determine the modulus of elasticity of the brass if that of steel is 2 times 10 raised to the power of 5 newtons per square millimeters. So, ladies and gentlemen, welcome as we solve this problem that we got here. Now, we know very well that the Young's modulus of elasticity is given by the ratio of stress to strain. And in this case, stress is given by load divided by the cross-sectional area. Now, starting with the steel rod, we are going to determine this is the load that is suspended to both wires, area of the steel rod. And in the same case, strain is given by change in length divided by the original length. Now, we need to determine the value of the load P. So what we are going to do, we are going to substitute this stress, this P over A here, and then the values of stress, the values of strain, we are going to substitute them at this point. And this is what we are going to have. The Young's modulus of elasticity will now be given by stress, which is rod over area, divided by, which is change in length, divided by the original length. This will lead us to load over area times the reciprocal of change in length over original length, which is length over change in length. And therefore, the Young's modulus of elasticity will be given by this relation. Load times original length divided by area times the change in length. We need to make P the subject since we don't have the value of the load. So when you make it the subject, since we are going to get its value. And in this case, when we make load P B to be the subject, we are going to have Young's modulus of elasticity times area times change in length divided by the original length. We are going to use the Young's modulus of elasticity of steel. We multiply by the cross-sectional area of steel. This is the change in length in steel. This is the original length of the same steel. Now, in this case, we are going to begin with determining the cross-sectional area of the steel member. And in this case, we are told that the diameter of the steel section, the steel wire, is 3 millimeters. Therefore, its area will be given by pi over 4d squared. This is going to be pi over 4 times the diameter, which is 3 millimeters. So 3 squared. That's going to give us an area of 7.0686 square millimeters. So that is the area, the cross-sectional area of the steel wire. So we are going to input those details in this formula. And in this case, we are going to have load being equal to the Young's modulus of elasticity of steel, 2.0 times 10 raised to the power of 5. We multiply this by cross-sectional area of the steel wire, 7.0686. Then we multiply by the change in length. it is extended by 0.75 millimeters. So that is the change in length. Then we divide this by the original length of the steel wire, which is 2 meters. We convert to millimeters, and that's going to give us 2000 millimeters. And in this case, when we carry out that calculation, we are going to get a load of 530.145 newtons. So that means that when a load of 530.145 newtons is applied or is subjected to this steel wire, that is what will happen. It will elongate by 0.75 millimeters. Now, after getting the value of the load, we are now going to use this amount of load to determine the Young's modulus of elasticity of brass. And in this case, we're going to apply this formula of Young's modulus of elasticity will be given by the load times the length of the brass wire divided by the cross-sectional area of the brass wire times the elongation of the brass wire when this rod of P is suspended on that brass wire. Now let's begin with determining the cross-sectional area of the brass wire. And this is going to be pi over 4 times the diameter of the brass wire is 2 millimeters in diameter. So that is going to be 2 squared. And this is going to give us an area of 3.14 square millimeters. So that is the cross-sectional area of the brass wire. Now, applying the formula, the Young's modulus will be given by a load of 530.145 newtons multiplied by the length of the brass wire, which is 2.5 meters, convert it to millimeters. That is going to be 2,500 millimeters. Then we divide this by cross-sectional area of the brass wire, that is 3.14 square millimeters, times the change in length of the brass wire. It is elongated by 4.64 millimeters. So we divide that by 4.64 millimeters. And when we do so, we are going to get Young's modulus of elasticity of 90,967.6655 newtons per square millimeters. Now, if you write it in standard form of 10 raised to the power of 5, just like the Young's modulus of elasticity of steel, we are going to have a Young's modulus of 0.90967 and so on and so forth times 10 raised to the power of 5 newtons per square millimeters. Therefore, ladies and gentlemen, that's how we go about. So that is the Young's modulus of elasticity of brass. So thank you very much, ladies and gentlemen, for watching our content. And if you are ready to subscribe, please hit that subscription button. We are going to appreciate it. Let's meet in yet another lesson. Thank you.